Okay, guys, we're going to continue along with chapter 7 today. So really important that the last two sections, mole ratios and calculations involving mass and the mole ratio, that we know how to do those, because everything we're going to do the rest of the way in this chapter is based off of those. So today we're going to talk about something called the limiting reagent. Sorry, because what we saw so far is that if you have this amount and this amount, these exact amounts, then we could make the reaction happen. This is exactly what you get. Well, it's really hard to try, and if we were in the lab, you would see this, to try and measure out exactly that amount and make sure you get it all out and not get stuck in the pan and all that type of stuff. So what we do is we tend to usually take a little bit more than we need of each reactant that we're using. Now, one of them, if we have two reactants, one of them is always going to be even more left over. Right? The reaction will take place and it'll continue until one of the reactants is completely used up and the other reactant, there's still a little bit left. So that one that's a little bit left, we call the excess reagent. And I don't know why they call it reagent, not reactant, but that's what they call it. So there's an excess reactant. The other one is what we call the limiting reactant. And that's the most important one, because when the limiting reactant is completely used up, the chemical reaction stops. Okay, so we need to figure out which one of the two things we're dealing with is the limiting reactant, because that's the one that's going to determine how long or how much of the reaction or how much of the reaction is going to take place. Okay, so that's what they are. The common practices are, if you're using an expensive chemical, like one of the ones we can use in our lab is silver nitrate. And silver nitrate for 50 milliliters or 100 milliliter bottle is like $66 or something. It's really expensive. So for us to do a whole lab with it and we can use a lot of money. So if you're doing an industrial process and you're using silver nitrate, say for example, a really expensive chemical, you want to use just barely what you need and have more of whatever else it's reacting with. That way you want to use up all that silver nitrate because it's really expensive. Where a common example is you put copper wire in it, we get a single displacement reaction. Copper wire is super cheap. It's pennies, as opposed to something that's really expensive. So we always would want to make, in industry, we'd always want to make the silver nitrate the expensive reactant, the limiting one, so all of it gets used up in our reactions. That way we just have some excess copper. It doesn't cost much. So that's a practical example of what we do. Okay, so we're going to look at a quick example here where if we take tin 4 chloride and add it to magnesium, we're going to get this reaction right here. Okay, tin 4 chloride plus magnesium gives titanium, not tin, Ti. Titanium 4 chloride and magnesium gives titanium and magnesium chloride. So the first thing we always need is that balanced chemical equation, always. Without the balanced chemical equation, our mole ratios aren't correct, and therefore we're not going to be able to do the question. So what they're asking us is if we have 2.8 moles of titanium 4 chloride and 5.4 moles of magnesium, how much titanium metal could I make? Okay, well, with this particular reaction, I've got to figure out which one of these two. Is this or is this the limiting reagent? Which one is going to run out first? Okay, so when I find that out, then I'm going to use that particular amount, whichever number of moles is limiting the reaction, to find out this one over here. Okay, so this is an important point. In this question, because it's our introductory question, we already know the number of moles of both reactants. Normally, that if they give us masses, we'd have to find the number of moles first. Okay, but we don't have to do that because we've got the number of moles of each one, 2.8 and 5.4. So we can go right to our ratio, right? Our ratio of tin 4 chloride, 2.8. So we're going to figure out if we use 2.8, it doesn't matter which one you start with. We're going to say right now, if we have 2.8 moles of titanium 4 chloride, how much magnesium do I need? Our ratio is 1 to 2. So here's my calculation. If I have 2.4 moles of titanium 4 chloride, I multiply by 2 moles of magnesium per 1 mole of titanium 4 chloride, because it's a 2 to 1 ratio. That's going to give me 5.6 moles. Okay, so this is telling me that if I have 2.8 moles of titanium 4 chloride, in order to use all this up, I'm going to need 5.6 moles of magnesium. Go back and look. Do you have 5.6 moles of magnesium? No, you've only got 5.4 moles. So if you don't have enough, then magnesium is the limiting reagent. All the magnesium is going to get used up first, and the chemical reaction is going to stop. There will be some extra tin 4 or titanium 4 chloride left over. Okay, so now we know this is the limiting reagent, which means that's the one we're going to work with. Now we don't worry about this guy at all. Okay, we don't have to worry about that guy. We're going to worry about this number right here. So now we're going to say, okay, if you have this many moles of magnesium, how many moles of titanium can you make? Same thing, 2-to-1 ratio. So here's my, oops, sorry, I rubbed some of it out on this. This says 2 moles of magnesium down here. So here we go. Now we take the number of moles of magnesium, because that's my limiting reagent, 5.4, times 1 mole of titanium over 2 per every 2 moles of magnesium. That's my ratio I get from 2-to-1. Do my calculation, 2.7 moles of titanium, right? Moles of magnesium would cancel. 5.4 times 1 divided by 2, 2.7. So if I had 5.4 moles of magnesium, I could make 2.7 moles of titanium. And you can kind of see that because it's 2-to-1, so this is going to be half of this. But the key is I got to determine which of these is that limiting reagent. Which one is going to get used up first in that chemical reaction and essentially cause a chemical reaction to stop. Okay, now that's the easiest version of these type of questions because they gave us pretty much everything. So let's look at one that's a little more likely, where if we take carbon monoxide gas, actually, sorry, I'm going to stop this one and get a new whiteboard marker because mine's dying, and then I'll do the other type of question in 1 second. Okay.